Okay, let us begin the class for the statistical physics for my master students. We had been studying the canonical ensemble formalism, and in that we had studied a bit regarding the distribution function. I would like to further emphasize on the fact that we had been studying microcanonical ensemble, the canonical ensemble, and right now we are trying to we have already derived also the thermodynamic properties, and from there we could see that we can arrive at the same thermodynamic parameters which are mathematically the same, and they should be the same because physically all should point to the same real physical systems. But then the question arises that how come for microcanonical ensemble, where we have a condition for energy variation within a small interval from E minus delta to E plus delta, and there the states, microstates, were defined by number, energy and volume of the system, and in the case of canonical ensemble, where we have the energy to be replaced by temperature, which is a fixed parameter, and energy can vary from 0 to infinity. In spite of all the different starting parameters, in one case in microcanonical ensemble we have NEV, the number, the energy of the particle and the volume of the system, and in the case of canonical ensemble we have the number, the volume and the temperature. Both leads to mathematically same thermodynamic parameters. What is the reason? We would like to derive mathematically the basic reason, and the physical reason is very simple, that when you are taking a large number of particles, which is the case with statistical physics, then they converge to the same value. So let us try to see how one can arrive at that by calculating the fluctuation in energy. So we are trying to derive the energy fluctuation that can be derived very easily by noting the fact that the internal energy or the mean energy of the system can be given for the canonical ensemble U as summation of ER e to the power minus beta ER divided by summation of e to the power minus beta ER summation over R, and this can be written as if one wants to write average value of the energy, which is U, and if we want to write this in terms of if we take a differentiation of the mean energy with respect to beta, what do we get? We get something like summation of ER square, okay, this should be minus e to the power minus beta ER divided by summation of e to the power minus beta ER, and minus of 1 by summation of e to the power minus beta ER square, okay, and then summation of ER e to the power minus beta ER, and then the differentiation of this, which is again going to give us e to the power minus beta ER, okay, and then it's going to give us multiplied by, if this is to be multiplied with this, then this is going to give us again summation of, so differentiation of this is summation of e to the power minus beta ER into ER, okay. So basically what we can get from here is something like, if we take minus of del u by del beta, I take the minus sign over here, then this is something like minus of ER square average, the first term, and the second term would be, okay, minus is taken on this, so this would be plus, and this is going to give us minus or minus, so this is again a minus sign over here, so this is going to give us minus minus plus and then again minus, so this would be equal to ER square, and this is ER average square. So this is basically the fluctuation in energy, which can be written as, we would call this as E square and E average square. So this is nothing but the fluctuation in energy, and if we want to take the root mean square fluctuation, so this is nothing but delta E square average, and if we want to take the root mean square fluctuation, then RMS fluctuation, root mean square fluctuation would be equal to delta E average square to the power half, and relative, if you want to take the relative, then you have to define or divide it by average of E. So now what is delta E square? Delta E square average is minus of del U by del beta, which gives us beta is 1 by kt, so that is going to give us something like kt square del u by del t, and that is equal to kt square cv. Now cv is proportional to n, so what we can say is root mean square fluctuation of energy is proportional to, so root mean square relative root mean square fluctuation in energy is given by delta E square to the power half divided by E, so that would be equal to since CV is proportional, so this is something which is proportional to n, the number of the particles, since as CV is proportional to n, so this is going to give us n to the power half, and energy is nkt, energy is proportional to, the mean energy is proportional to n, so this is equal to 1 by n to the power half. So basically the root mean square fluctuation in energy is of the order of n to the power minus half, and that proves the fact that as the number of the particles are increased to a huge number, then the corresponding fluctuation in energy is minimized, and both the canonical formalism and the microcanonical formalism leads to the same result in terms of deriving the thermodynamic parameters. Okay, let us apply the canonical ensemble formalism to derive the principle of equipartition of energy, or the equipartition theorem. For that, we need to take the expectation value of a quantity which is xi del h xj, where xi and xj are the phase space coordinate. Phase space coordinate are those like the coordinates and the momenta, which we know. There are 6 n-dimensional coordinate for n independent particles, and we need to calculate this, the expectation value of this. So under canonical formalism, we can mathematically write this as equal to xi del h del xj e to the power minus beta h, where h is the Hamiltonian, into d omega e to the power minus beta h d omega, where d omega is basically equal to the elementary volume in the phase space, which can be written as d3nq d3np. Okay. Now, in order to evaluate the numerator, we can always write xi del h del xj e to the power minus beta h to be equal to minus of xi by beta del of xj e to the power minus of beta h. You can see that this is going to give us the same value as this. So if we substitute this in the numerator over there, we can write the numerator part to be equal to minus the numerator of the part is equal to minus of 1 by beta, and xi del of xj e to the power minus of beta h, okay, and d omega. So if you want to integrate this by parts, then you can write this as equal to minus of 1 by beta. So integrating by parts with respect to xj, because here the variable is xj, so we can write minus of 1 by beta xi e to the power minus beta h xj1 to xj2 and d omega j. This is the first part, and the second part can be written as 1 by beta. There would be a negative sign, so plus of 1 by beta, and then del xi by del xj, okay, and then e to the power minus beta h and dxj d omega j, where xj1 and xj2 are the extreme values of xj, and d omega j is nothing but the elementary volume d omega devoid of dxj, because we are taking the integral variable as dxj, so we have another part multiplied with that as d omega j. So dxj into d omega j is again returning back d omega. How about the first part? When you take the extreme values, then extreme values at extreme point, the kinetic energy would be infinite and the potential energy would be infinite. So each of x1 is equal to infinity and each of xj2 is also equal to infinity. So that makes the first term to be 0, e to the power minus infinity, that goes to 0, and we are left with only the numerator part as 1 by beta, and del xi by del xj is delta of ij e to the power minus beta h and d omega, because d omega is dxj into d omega j. So if we substitute this numerator over here, then our expectation value of this actually settles down to something like 1 by beta delta of ij exponential minus beta h d omega divided by exponential minus beta h d omega. So this and this cancels out and we are left with kt delta ij. Now for a special case, for xi is equal to xj is equal to pi, p the momentum, then we can always write p pi del h del pj, which gives us pi qi dot to be equal to kt for I equals to j, so pi qi dot is kt. Similarly, for xi is equal to xj is equal to qi, again we have qi del h by del qi, which is equal to minus of qi pi dot, which is again equal to kt. And if we take a summation over all the degrees of freedom, then we can always write summation of I is equal to 1 to thrice n, and then pi qi dot to be equal to thrice n kt, and similarly I is equal to 1 to thrice n if there are thrice n degrees of freedom, minus of qi pi dot to be equal to thrice n kt. Now we can always take a Hamiltonian and a suitably or a canonically transformed Hamiltonian in terms of new coordinate, such that the Hamiltonian is quadratic in both the coordinates of the phase space. One is the generalized coordinate and the other one is the generalized momentum. Let us do that. Now, by a suitable choice of the canonical transformation, we can always write a Hamiltonian which can be written as summation of j aj pj square plus bj qj square, where capital Pj and capital Qj are the transformed canonical coordinates, and then hence one can very obviously write that summation of aj summation of pj del h del pj plus qj del h del qj, then this should be equal to twice of h. One can very easily verify from here, because you take del h del pj, it would be twice aj pj and del h by del qj, and then you multiply it, so 2 of aj pj square plus 2 of bj qj square, and that is going to give us twice the Hamiltonian. And now you take the average, taking average of both sides, average, then we can write summation of pj del h del pj plus qj del h del qj. Okay, then that should be equal to 2 of summation of the average of the Hamiltonian, which is going to give us the average of the Hamiltonian. And obviously the left hand side is equal to thrice n kt plus thrice n kt, and this should be equal to twice of h, or average of h is equal to 6n kt by 2. Since the number of the degrees of freedom in this particular case were taken thrice n, that's why it becomes, because we have taken thrice n degrees of freedom, so we have taken the summation from I is equal to 1 to thrice n. And if there are f degrees of freedom, for f degrees of freedom in general, we can always write summation of h to be equal to fn kt by 2, which proves the principle of equipartition of energy, or equipartition theorem, which says, according to which the average energy is equally partitioned among the different degrees of freedom, and per degree of freedom the energy is equal to half of kT. Okay, 6 n degrees of freedom, so this should be, sorry, so if there are degrees of freedom, there were 6 n degrees of freedom, so there it was 6 n kT by 2. So per degree of freedom the energy is equal to half of kT. Thank you.